class with the mic. All right, so it's going to be chapters 7 and 8. Listen, guys, I'm going to recover sort of everything in brief, just sort of recap all the topics, and then if y'all have questions, we can go through them then. So in chapter 7, first you just need to know all those definitions. Guys, in chapter 7, the signs really get you, so you want to make sure that you know what the signs mean, because as you notice in the questions when you go through, there are certain things that might be negative, but I don't say they're negative, like things like image distance and focal length and magnification. So you need to know what those things mean in words. So for example, if an image is inverted, that means its magnification is negative. For example, if I have a convex mirror, that means its focal length is negative. If I have a virtual image, that means its image distance is negative. So you need to know what those things mean in words and be able to interpret them and apply the right signs. So students often mess up in that way. So just to recap that, if I have a negative image distance, that means it's a virtual image. If I have a positive image distance, that means it's a real image. If I have a negative magnification, that means it's inverted. If I have a positive magnification, that means it's upright. And if I have a convex mirror or a concave lens, that is a negative focal length. If I have a concave mirror or a convex lens, that is a positive focal length. So just knowing what those signs mean will help you. For flat mirrors, so we have, well, let me go and sort of write down our equations. We don't have many equations here. We have our magnification is negative Q over P. Also our magnification is HI over HO. Now if our image is inverted, this HI will assume to be negative, right? So if the image is upside down, the image height is negative, which gives us a negative magnification. So that's how that plays in. Also, we had the lens and the mirror equation. Both of these are the same. 1 over F equals 1 over Q plus 1 over P. And the focal length is 1/2 the center of curvature. That's the radius of the object. And I think that's it as far as equations. Yep, that's it. So the equations are pretty simple, but applying them is not so simple. You will, or you could, I haven't made up the test, but you could have a system of equations. That is one where you have to substitute this equation into this equation. That's not terribly difficult. You had a homework problem. We had some problems in class like that too. So just be prepared for that. So for example, where you would have, say, the magnification and the focal length, and you have to solve for Q. Well, we had a problem like that in class, where then you would have to say P is equal to Q over M, and then plug that in here for P, and then solve for Q. We can look at that later if you want to look at an example like that. All right, let's go through the mirrors first. For flat mirrors, pretty simple. P is equal to negative Q. It's always a virtual image. The magnification is always equal to +1. These are always virtual images. Flat mirrors only produce virtual images. The spherical mirrors are really the ones that are difficult. Go down. Okay. Sorry. Is that okay? Can I go down? Looks like y'all are writing furiously. Pretty much. Yeah. Okay. I am going to put this online, so if you miss something, I'll put it on YouTube soon, okay? All right. Concave mirrors, convex mirrors. Concave, convex. Listen, knowing the ray diagrams will really help you in this. Honestly, you're only going to have 1 or 2 questions about the actual ray diagrams, but just knowing what the ray diagrams look like will help you to answer some of the other questions, because you'll also have questions about this type of mirror produces this type of image. What kind of mirror is it? And we worked some problems like that in class. So just knowing the type of images that the mirrors form will help you. So a concave mirror produces 3 types of images. If the image is inside the focal point, it makes if the object is inside the focal point, it makes an image that is virtual, upright, and bigger. It's virtual, upright, and bigger. It's a virtual image, it's upright, it's bigger. That's like your makeup mirror when you hold it really close to your face. Concave mirrors, if the object is at the focal point, there's no image at all. Mathematically, we would say that Q is equal to infinity. And so if F equals P, it turns out that Q is undefined in your calculator, or it's equal to infinity. And then the other one is when the object is outside the focal point. In this case, our ray diagrams give us an image that looks like this. I'm not drawing the ray diagrams here, I'm just sketching out the images, but you do need to know how to draw those rays. As I said, you'll have 1 or 2 questions where I'll just show you a series of rays and ask you either which one is correct or incorrect. So we've had sample problems like that before. You could have one similar or different, obviously. This is a real image, it's inverted, and it can be either bigger or smaller. So we'll just say that it's real and inverted. With convex mirrors, you only get one kind of image. There's my focal point. Remember, in convex mirrors, by the way, they have a negative focal point. Concave mirrors have a positive focal point. This is my object. My image is here. An image in a convex mirror is always virtual. It's always upright, and it's always smaller. Convex mirror always a virtual, upright, smaller image. So in some problems, for example, and I think we worked one like this in class, I gave you a word problem where I said that this mirror, we don't know what type of mirror it produced, but it made a virtual image that was half the size of the object. That has to be a convex mirror, because in no way does a concave mirror produce a virtual and smaller image. The only time it produces a virtual image is when it's a bigger image. So you can see a problem like that. You probably will see a problem like that where I don't tell you what kind of mirror it is, but it's very important for you to know what type of mirror it is, especially here because the focal length is negative. And so if you take the focal length to be positive in such a problem, then you get it wrong. All right, so you really got to know these mirrors, and knowing this little page will help you a lot to the end of this. Okay, I'm not going to work through problems here, but if you want, we can go back. And likewise, I'm not going to draw the ray diagrams, but you are responsible for knowing those. I think once you get those rules down, well, it's not trivial to know them, but just practice. Okay, we had 2 different phenomena, the atmospheric refraction. Atmospheric refraction means that the sun appears even though it's already dropped below the horizon, and that's due to refraction. So atmospheric refraction, you just need to know the effect of it. The effect being that the sun appears even though it's already below the horizon, and you need to know what causes it. It's caused by the refraction of the sun's light in the atmosphere. So atmospheric refraction, sun appears, or the sun is visible below the horizon because of refraction of the atmosphere. All right, the other thing that we had were mirages. Mirages, the effect is that it appears that you see water, or you think it's water because it appears that there's a reflection in the road or in the desert or wherever you happen to see this mirage. And the reason that this is because the hot air refracts the light. There's our figure in your book that shows how this happens. But the hot air refracts light, and that makes it appear as if there is a reflection. You could have 1 or 2 questions, just basic. How does this happen, or what does this cause, or some combination of that. All right. Now moving on to lenses, we had convex lenses and concave lenses. Be careful because convex lenses act like concave mirrors, and concave lenses act like convex mirrors. Right. So if you want to think about them, convex and concave refer to the shape, but convex lenses are a converging device, concave mirrors are a converging device. That's why they act similarly. Yeah?
Because of reflection or refraction?
Refraction. Yeah, that's not a very good abbreviation, is it? Yeah. Okay, refraction. Okay? I go down from here, y'all? I know this is fast, okay, I want to cover all those chapters, and I still have some time. So lenses, we had convex, these have a positive focal length. Concave, have a negative focal length. All those equations that we did for mirrors, they apply here in pretty much the same way. The only difference is that, well, what's some of the differences? If I have an object over here and I have an image over here, this is a real image. That was different for mirrors, right? For mirrors, if the image was on the opposite side of the object, that would be a virtual image. You follow me on that? Okay, but for lenses, it's different. If they're on the opposite side of the lens, on the opposite side of the object, then that's a real image. Okay, let me step through the different images that these are formed. You'll need to know how to draw the ray diagrams again for these. It could be that you have one mirror and one lens, or you might just have one ray diagram at all. I'm not sure. But it helps you to know, nonetheless, the types of images that are formed by convex and concave. This is concave. It caves in. That's why it's called that. This is convex. I don't know why it's called that, because it's vexing, I guess. If you have it outside the focal point, the object, you produce an image, a real inverted image that could be either smaller or bigger. This is the image. If you have it at the focal point, it produces no image at all. And if you have it inside the focal point, this is the object, the image looks like this. All right, this is a virtual, upright, bigger image. Virtual, upright, and bigger image. For our concave lens, let's see, I forget this. Yeah, concave lens, if your object, if my object is here, my image is here. Concave lens, just like the convex mirror, all right, produces a virtual, upright, smaller image. All right. Remembering some of these, just to remind you, this would have a positive image distance. This would have a negative image distance. And this would have a negative image distance. All right, that's different from mirrors. If this were a mirror, this would be a negative image distance. So mirrors and lenses are very similar because they're both spherical, and it's really just a geometry thing that we're dealing with, and that's why they're so similar. But some of the notations are different for signs. What's real, what's virtual. All right, you will have a two-lens system. Can I go down from here? You'll have a two-lens system. In that, you have two sets of focal points. If I have an object out here, my image looks like that, and this distance becomes the object distance for the second lens. We worked through a couple of these in class, and you have some in your homework. And then you can find your image, your second image, and the final image, which is out here. So this is your original object over here. This becomes your image from your first lens. This image from the first lens becomes the object for the second lens, which is here. And so this becomes our object distance, and then we can find our image distance. So I can also find my magnification, that's going to be negative Q1 over P1. And our second magnification, negative Q2 over P2. And if we want to find the total magnification, it's just M1, M2. All right? Not going to have a virtual object on this test. That means that you're not going to have it so that your lenses are really close together like y'all had in lab. I think y'all did that in lab, right, when they were close together and you had to deal with a virtual object. I'm not going to do that in this test. They'll be spread out like this. So don't worry about the negative P. That's what I'm saying. All right. Then we had aberrations, spherical aberrations, and chromatic aberrations, and that was it for this chapter. So spherical aberrations, you need to know what causes them and where they occur and how to fix them. Spherical aberrations, chromatic aberrations. This is caused by the spherical shape. Chromatic aberrations is caused by the dependence on wavelength of n. Remember, I draw this figure. It looks like that. So for short wavelength light, that would be blue. You have a lot of refraction. For red light, you have not as much refraction. Ways that you can fix this for spherical aberration, you can either use an aperture to blocks the rays on the outer parts of your device, or a parabolic mirror. And this occurs because it doesn't have anything to do with refraction. This occurs in mirrors and lenses. All right, chromatic aberration. In order to get rid of this, you have to use a system of lenses to minimize it. It's a little more complicated, but we'll just say that. Use a system of lenses. And this is only in lenses. Because you don't have refraction in here, so only in lenses. All right, so that was chapter 7. We'll come back to that if you have questions, okay? But I want to go on to chapter 8. Chapter 8, you need to know how interference works, constructive versus destructive interference. You also need to know how to describe when two waves are out of phase. So if I have two waves that are like this, these are said to be in phase. You'll certainly have a question like this asking you if waves are in phase or out of phase. Also, you need to know when they're out of phase by how much they're out of phase. So for example, if I were to give you these two waves, you would tell me that these two waves are 0, 90, 180, or 360 out of phase. And you would say, not 360, 180. You would say that these are 180 degrees out of phase. You could also say that they're out of phase by half a wavelength. All right? So 180 or half a wavelength. In your calculus class, you might say that this is pi out of phase. It has a phase shift of pi. You'll do that in calculus, phase shifts? No? Okay. Maybe in Calc 2. Oh, yeah, okay. You don't take Calc 2, do you? All right. So you need to know that. Also, if it's a quarter wavelength out of phase, it's going to look a little funkier than this. That means that, let's see, this is a full wavelength, so that means that I'm going to start here so that my wave will look something like this. So the peaks don't line up with the peaks and the troughs don't line up with the troughs. This would be a quarter wavelength out of phase, or 90 degrees. We had some questions about this in the concept test and then also in the book as well. So knowing which waves are in phase or out of phase. We had some questions too about these waves and how they travel different path lengths. So for example, if I have a wave that travels a certain distance and it has a wavelength equal to say 4 meters, all right, and then I have a wave that travels another distance. Let's say this wave traveled, I don't know, 10 meters, and then I had another wave that traveled 8 meters before they met up again. That would mean that the next wave would start at 2 meters right here, and it would look like that. Would that be in phase or out of phase when they meet? Out of phase, because they're separated by half a wavelength. So you need to go back and look at those questions about path length difference, like the mountain question that we did in class, and we had some questions as well in the concept test about one wave has a wavelength of this and it travels this distance, and another wave travels this distance. Then are they in phase or out of phase? Because that's very important when we get into double slit diffraction and understanding why double slit diffraction occurs the way that it does. You might also have some questions just sort of about that. You've seen this in old tests if you've looked at them, where I show you a double slit apparatus setup and ask you, what is the path length difference for these two waves, and what is it at this spot where you see a bright spot, and where is it at this spot where you see a dark spot? We had some problems like that in class, and you'll certainly see some on the test. You follow what I'm saying about that? We'll come to that in a second. Let's look at double slit. So in the last part of this chapter, we had double slit, single slit, and diffraction gratings. You're likely to see more double slit and diffraction grating problems. You will see one single slit problem, but it's just sort of, I don't know, to make sure you know how to do the single slit. Single slit's a little bit different. Just make sure you know how to use the equation. The equation is a little bit different from the others for the double slit and the single slit and the diffraction grating. Let's look at the double slit. We have two slits like this. On the screen, you get a really bright spot in the middle, followed by a dark spot, followed by another bright but dimmer spot, followed by a dark spot, and on and on. This we call our 0th order. We might call it a bright spot, might call it a fringe. What else do we call it? I guess that's it, a bright spot or a fringe. But that would be our 0th order. This is our 1st order. M equal 1, M equal 2. As we did in class, you also need to know what is the path length difference for these various bright and dark spots. So for example, here my path length difference between the waves that originate here is equal to how many wavelengths? 0 wavelengths. That's why you get complete constructive interference, because there's no path length difference. Whereas here, I get a path length difference of a half a wavelength. 1 wavelength, 1.5 wavelengths, 2 wavelengths, and on and on. So that's that path length difference. Remember, we had a figure in class where I show the paths to these different things. So for example, this distance, this physical distance in this double slit would equal to 2 wavelengths because it goes to the 2nd order fringe. That extra little distance is 2 wavelengths, and that's why you get constructive interference there. You need to, of course, know how to calculate these distances. For example, to the 1st fringe, you would need to know how to calculate y. These equations are on your equation sheet, but you need to make sure that you look at that because they're not labeled. They come in the order that we cover them. Double slit, single slit, diffraction gratings, but just make sure that you look at it and you understand what those mean before you go into the test. We know that d sine theta equals m lambda. D sine theta, that's just that path length difference, and this is just the requirement for constructive interference, that you have to have an integer number of path lengths, integer number of wavelengths in order to get constructive interference. Okay, this starts at 0, 1, 2, and on and on. Also, if I want to know y, not like y like WHY, but you know, like the value y, I notice that I have a triangle here. Say if I'm finding it to the 2nd order fringe, this angle is theta. That's the same, by the way, as this angle. There's some approximation there, but we assume that that angle is theta. This is L, which is usually given, and this is Y. So notice that I have a triangle here, a right triangle. And so I can say that the tan of theta equals Y over L. All right, and I can solve that then for Y, to find Y. Also, you need to know how to find out the maximum number of orders. The maximum number of orders for all of these, the double slit, single slit, and the diffraction grating, the max number of orders arises because theta exceeds 90 degrees. Once this angle theta gets bigger than 90 degrees, that means that that light is no longer going to show on the screen anymore. So here, if light goes in this direction, theoretically it'll go onto the screen, but if it goes past 90 degrees, you're never going to see any orders. In practice, actually, you don't see that many orders, but theoretically, that's how we find the max number of orders. Okay? You with me? Is this really exciting? Because you look excited. Okay, a couple more things. As I said, single slit works the same way, just a little bit different. You get a similar pattern. It's actually not quite the same, but that pattern is governed by this expression, A sine theta equals m lambda. But remember, this is for dark spots. So on the equation sheet, it says that this is for dark spots, but it doesn't say that it's for single slit. So just make sure that you're aware of that. And also the other difference is that M is 1, 2, 3, dot, dot, dot. That's because when you're talking about single slit, you don't talk about the central or the zeroth order, that you start here. This is M equal 1, this is M equal 2, and on and on. And by the way, it is symmetrical. I have asked this question, how many bright spots, dark spots there are on the screen. So make sure we did a question in class like that. Make sure you're not thrown off by that because it is symmetrical. So like for example, if you calculate a maximum order of 2, then that means 5 spots because you have 2 spots on either side and then you also have that zeroth order, that central spot. This is single slit, yeah. Oh, let me go back. This is on your equation sheet, but this is for bright spots. But remember, if I want to find dark spots, it's d sine theta. That's my path length difference. M plus 1/2 wavelength. That's my criteria for destructive interference. That is offset by 1/2 a wavelength, or some integer value of path wavelengths. 1/2, 2/2, or 3/2, 5/2, on and on. And then diffraction gratings. Diffraction gratings work exactly like double slit diffraction for a similar reason, because of the geometry. But the other addition is that you'll often have to find D. And so, for example, if I have a diffraction grating with 1,000 lines per centimeter, then I would find D as 1 over 1,000. That's 0.001 centimeters. That's going to be 0.00001 meters. Make sure you know your metric prefixes, of course. Centimeter is 10 to the minus 2, so I move that decimal place 2 spots. Millimeters, which you could also see, is 10 to the minus 3. And nanometers, which comes up with wavelengths, is 10 to the minus 9. Make sure with all of your diffraction gratings, your double slit, single slit diffraction, that everything is in SI units. It won't be given in SI units just because those numbers don't really make sense in meters. But when you calculate these various things, they have to be in meters. Also make sure your calculator says frequent. Okay? Otherwise, the diffraction grating is exactly the same. And then the very last topic was the diffraction grating. Yes, I'm sorry. So you find the bright and dark spots in the same way. That's just d sine theta equals m lambda, where m is 0, 1, 2, dot, dot, dot. Okay, remembering to convert everything to proper units, SI units. All right. Oh, and then there was just the Fraunhofer diffraction, the circular diffraction, where you get that circular diffraction pattern. No, it exists, really. We didn't really go into much detail on that and how it works. But it works in much the same way as the double slit diffraction, but just know that, just a second, Tom, when you shine a bright light on a circular aperture, instead of getting a circular shadow, that you get a diffraction pattern instead. John? Oh, for double slit, it's d sine theta equals m plus 1/2 lambda. That is on your, and the orders are the same too. That's on your equation sheet. Again, this is the path length difference. Just geometrically, that's how it comes out. This is the requirement for destructive interference, that you're offset by 1/2 wavelength. And so in order for those to be equal, or in order to have dark spots, those have to be equal. All right, that's all the material. I can go over old test if you like. Questions. You want to do that? Look at some old test questions? All right. If you feel like you have this, it's okay. You can, we can just treat this like a help session. You can get up and go if you like. All right. Don't forget, there is a quiz on Friday. Oh, this is a good one. You have a good day, folks. All right, this is last year's exam, which was largely everything we're doing on this exam. All right, let's see. There's some ray diagrams. Those were examples sort of knowing what's right and what's wrong. Let's just sort of take a quick look at some of these. Here's a word problem where you have to find the focal length of the mirror. This was a two-lens problem. Some stuff about spherical mirrors, aberrations. Here's another word problem. This one's a little more complicated. We can come back and look at this one. This was like a homework problem that you had, number 14. Know about the eye, the difference between the eye and the camera as well, y'all. We talked about this. Remember the eye, the image distance is fixed, the focal length changes. For cameras, the focal length is fixed, but the image distance changes. We'll come back and look at this, I think. And then mirages and flat mirrors. Is that all we have in that test? I guess so. Any one of these particular questions? We'll look at this one, number 11. Is that one okay? This one looks a little tricky. Okay, this one says a mirror produces an upright image of an object. The object is 4 centimeters high, the image is 2 centimeters high. So remember, this is the one that I was warning you about. You want to look at this problem, the first thing you want to ask yourself is, gosh, what kind of mirror is this? And then you would say, well, the image is upright, and upright images are always virtual, right? Because in order for an image to be upright, that means its magnification is positive. That means that Q has to be negative for the magnification to be positive. So I have a virtual upright image, and it's smaller. And then I say, oh, this mirror is a convex, right? So this is a convex mirror. So that means that my focal length is negative 20 centimeters. It's a convex mirror because my image is upright, virtual, and smaller. Remember, a convex mirror, that's like your security mirror. So my focal length is negative 20. I can also find my magnification. My magnification is HI over HO. That's 2 over 4. That's equal to positive 1/2. That's all I know. All right, so this is also a system of equations, which you could also see. And I want to know what is P equal to. So I have two equations. I have 1/2 equals negative Q divided by P. And then I also have my lens equation, 1 over negative 20 equals 1 over Q plus 1 over P. All right, 1 over P plus 1 over Q, or whatever. All right, and then I want to solve this. So this is a system of equations, but it's not a terribly complicated one. I'm looking for P. That means the equation on the left, I want to solve in terms of Q. So I get something that only has P in it. So I cross multiply, and I get 2Q equals negative P, or Q equals negative 1/2 P. And then I take this, and I put it in up here, and I get negative 1 over 20 equals 1 over P minus 2 over P. Y'all follow what I did there? This became 2 over P because I had 1 over negative 1/2 P. I just bring the 1/2 up, and it becomes 2 over P, and it also becomes negative because of this negative. Probably going to have a system of equations like this. A problem similar to this. It'd be like this, honestly, because they're just, work this 12 times so we can have it down. Okay? I mean, it's not going to be exactly like this, but the numbers will be different. But it'll work out much the same way, where I'm solving that magnification equation for one value and plugging it into the other. John? Yes. This was last year, spring 14. Okay, and then I have negative 1 over 20 equals negative 1 over P, because 1 over P minus 2 over P is 1 over P. Those go away, and so P is equal to 20. See? Easy peasy, as they say. Doing your fractions will help you. I mean, you can do this in your calculator, but it's a lot easier if you just sort of do it with fractions. And I'll try to give y'all real easy numbers. Yes, y'all can do that, right? Like today, if I gave it to you right now, y'all can do that? All right, be prepared for that. You'll likely have a question like that. Can I take this away now? Go. Okay, let's see. Let's look at this human eye thing. The human eye has a lens that can change its focal length. When is the focal length of the eye's lens the largest? That's going to be when you want to think about the eye. If something is really far away, that means the light rays are coming in parallel and they're going to focus back at the back. That means that the focal length is right there. But if something is close up, the focal length gets smaller, and you can think about your ray diagrams, how you draw them, to produce an image that's on the retina. Okay, so your focal length of the eye's lens is largest when the object is far away. All right? Also think about the shape of the eye's lens. The eye's lens is really long and slender when you're looking at things really far away, and it's short and wide when you're looking at things up close. Because a lens with a long focal length is thin in the middle, whereas a lens with a short focal length is wide in the middle. That's why it's difficult for old people to see things up close, because their lens can't get wide in the middle. They can't squeeze it down. All right. Any other particular questions on here? We're running a little short on time. You need to know your different lenses, convex, concave, same for the mirrors. You could just have an identification. Anything in particular, y'all? All right, let's look. I didn't have diffraction on this test, so let's look at a previous. Let's see, spring 13 maybe? No. Spring 12. So we're going to have done diffraction in 2 years. Y'all done really well this semester. Like your grades are really good, like as a class overall. But we've covered 8 chapters. That's pretty good in this class. So I've been very impressed with y'all. Okay, so here's a good basic, and you'll have probably a couple of these. A good basic double slit, single slit. This one happens to be double slit, but you'll have a couple of these, either with double slit, single slit, or diffraction gratings, or all three maybe. But I have a laser beam that's incident on 2 slits that are 0.1 millimeters apart. How far is the second bright fringe? So the first thing I want to do is find the angle. So I say d sine theta equals m lambda. This is d. So d is 0.1 times 10 to the minus 3 because it's millimeters. Sine of theta equals m. M I get from this, so m equals 2. And the wavelength is 650 times 10 to the minus 9. So then I would solve that for theta. I get 0.74 degrees. All right, and then I want to find the distance. Remember, I'm looking at a triangle that looks like this. This is my angle theta, this is L, this is Y. So I say tan of 0.74 equals Y over L. This is L, which is 5. So Y is equal to the tangent of that times 5, which is 0.065. That's in meters, but in centimeters, that's going to be 6.5 centimeters. Knowing how to do your metric conversions on your feet, on the fly, will make this a lot easier. That you don't have to think a lot about and write out your little conversion tree or whatever it is up here where you do the just being able to say, well, this is 10 to the minus 2, this is 10 to the minus 3 or whatever. I think you're all probably at that point by now. You'll have a couple of those something similar to that. This, by the way, is spring 12. Can I take this away? Yeah.
How
Yeah.
about the shrinking reflection, you know, if it's one slit?
Okay, because it says two slits right here. Yeah.
So it's gonna say?
Yeah, it'll say. That's important though, that you get that right, especially between double slit and single slit, because it is different. All right, can I take this away? So yeah. All right, let's go through here. Diffraction gratings. All right, that's a very similar thing. How far apart are two adjacent slits on the grating? Oh wait, no, this is just asking for the distance d. So you will have to do this as well. To find the distance d, you just say 1 over 540. And if I take the inverse of 540, I get 0.0019. But that's in millimeters. So it has to be this, 1.9 times 10 to the minus 6. I would move it over 6, or yeah, that's not right. Did I do that right?
Move to the left.
Thank you. Yes. I move it to the left. So 0.0019, I move it over 1, 2, 3, so it's going to be 0.000019, 1.9 times 10 to the minus 6. Thank you, Carol. All right. You'll have one of those where I just give you the slit spacing. You have to figure out what is D for that. You'll have some of this. How are the waves in or out of phase and by what amount? You need to know both by wavelength and by angle. Oh, what is this, y'all? This is a half a wavelength, or 180 degrees. So it's either 2 and 4 is the answer. Y'all like those, like where there are multiple? I thought y'all liked those. Oh man, I've been giving them all year, just because I thought that y'all liked them. Okay.
And I've always one for sure, and I'm not sure about
You'll also have some of these questions. We had several of these on the concept test about what do you do to the slit in order to change the pattern. Go back to the concept test because we had several questions like that. Like if I want to make the pattern more spread out, what do I do to the width of the slit, or the separation between the slits? And that's a similar question here. In Young's double slit apparatus, by what factor is the distance between light and dark fringes changed when the separation between the distance is doubled? All right, so I say d sine theta equals m lambda. And then I also say that y equals L tan theta. All right, so if I double the separation between the slits, I'm keeping this constant. That means I have that angle theta. That means I'm going to have this, which means that this distance y is also going to have. So C is the right answer. Y'all follow that line of reasoning? If you're not entirely clear, go back to the concept test and look at this, because we did have this several times, and you'll see that on the test as well. All right. I think that the highest order, I showed you one of those. Remember, that's where theta equals 90, and you just solve for m. Any particular questions, y'all? We just have a few minutes left.
Questions take the test this week?
Similar to before, 25-ish. How many would you like to have?
25.
More than 25? But we don't have enough time.
what are the like simple concept ones?
The concepts don't take long.
Okay, I'll try to, I'll write it and then I'll add a couple of things. So you're thinking 27 questions? Even up like 30 questions? 30 seriously?
30. But like the last one, I
I'm
like.
given 34. This is my first semester here, the very first test I gave. I'm like, 50 questions. And I worked here, I'm like, oh, it took me 35 minutes. They didn't know to do this. Well, they were not very happy. They were not very happy people.
You enjoyed that.
No, I didn't know, it was terrible, I did, they hated it. It's the worst class ever.
How many questions have I?
It's gonna be, let's see, around
And you said this.
40 or 50. Yeah, that's okay. They'll be similar to this. All right, I always start with that as my base, and then I change them up a little bit. Just like last time. Remember last time? Okay? There we go. Tomorrow at 3, okay, if you want to come. Yeah, we'll be in Beauregard 165.